January 17th, 1945. Ardennes Forest, Belgium. The snow fell in silence. Heavy, wet flakes that clung to the splintered pines and blanketed the frozen corpses scattered across the hillside. A German artillery observer, Oberleutnant Klaus Müller, crouched in a shallow foxhole, his breath forming clouds in the bitter cold. His hands, stiff and purple beneath torn gloves, gripped a pair of Zeiss binoculars. Through the lenses, he watched American positions 2 kilometers distant. A maze of hastened trenches and supply depots carved into the white landscape. He had been observing these lines for 3 days now, waiting for the counterattack his commander's promise was coming. But something had changed in the last 48 hours. Something he could not name, could not explain, but felt in his bones with the certainty of a man who had survived 4 years of war. The sound came first. Not the familiar whistle of descending shells, that high-pitched scream that gave a man precious seconds to dive for cover. This was different. A series of sharp consecutive cracks in the air, like branches snapping in rapid succession, but amplified 1,000 times. Muller pressed himself into the frozen earth as the sky above erupted. The shells were detonating not on impact with the ground, but directly overhead, 20 meters above the treetops, bursting into perfect spheres of shrapnel that rained down with mathematical precision. Men who moments before had been crouching in trenches, protected by earth and timber, were cut down where they stood. The fragmentation patterns were unnaturally precise, as if some invisible intelligence had calculated the exact altitude to maximize casualties. In the span of 90 seconds, Muller's entire battery, 32 men who had fought together since Normandy, ceased to exist. He alone survived, shielded by chance beneath the overhanging roots of a fallen oak. When the barrage lifted, Muller crawled from his hole and surveyed what remained. Bodies lay scattered in poses of interrupted action, a gunner still gripping the lanyard of his howitzer, a radio operator frozen mid-transmission. But what struck Muller most was the distribution pattern. Every shell had detonated at precisely the right altitude to defeat their defensive positions. There was no waste, no randomness. It was as if the American guns could see through the forest canopy, could sense the exact moment to detonate for maximum effect. He had witnessed many horrors in this war, the firestorms of Hamburg, the meat grinder fillets. But this was something fundamentally different. This was not the application of overwhelming force. This was surgical, intelligent, impossible. That night, as he stumbled back toward divisional headquarters through the snow, Klaus Müller understood with absolute clarity that Germany had already lost the war, not because of numbers or industrial capacity, or even the two-front struggle that consumed the Reich. Germany had lost because somewhere across the Atlantic, in laboratories and workshops he could scarcely imagine, American engineers had unlocked secrets that made warfare itself obsolete as the Wehrmacht understood it. The rules had changed, and Germany was still fighting the previous war. The story of the proximity fuse begins not in the forests of Belgium, but in the bureaucratic corridors of pre-war Washington and the lecture halls of British universities. It is a story of desperate necessity meeting unprecedented innovation, of theoretical physics transformed into practical lethality. By 1940, Britain stood alone against the Nazi war machine. The Luftwaffe's bombing campaign had shifted from attacking RF airfields to targeting London directly, and British anti-aircraft defenses were proving catastrophically inadequate. Traditional artillery shells relied on timed fuses. A gunner would estimate the altitude of an enemy aircraft, set the fuse to detonate at that precise moment, and hope the shell passed close enough to the target. It was inexact science at best. Studies show that British anti-aircraft batteries were expending an average of 20,000 shells for every German aircraft destroyed. 20,000 shells. One aircraft. The mathematics of attrition were unsustainable. British scientists, working in secrecy at research facilities scattered across the countryside, had been attempting to develop a solution. The concept was theoretically simple. Create a fuse that could detect its proximity to a target and detonate automatically when it passed closest. But the engineering challenges were staggering. The fuse would need to survive the tremendous acceleration of being fired from a gun, forces exceeding 20,000 times gravity that would shatter conventional electronics. It would need to function reliably in temperatures ranging from Arctic cold to tropical heat, in rain and snow and dust. It would need to be mass-produced by the millions, cheaply enough to be expendable, reliably enough to work every time. And it would need to be small enough to fit inside the nose cone of a standard artillery shell. By 1940, British researchers had concluded it was impossible with existing technology. The components required: miniaturized vacuum tubes, reliable power sources, proximity detection systems, simply did not exist at the necessary scale. In September that year, as German bombs fell nightly on London, a British technical mission arrived in Washington, carrying their incomplete research. It was an act of desperation and trust. Britain was sharing its most sensitive military secrets with nations still technically neutral, gambling that American industrial capacity and scientific expertise could solve problems that had proven insurmountable in British laboratories. What the British mission discovered in America was not merely greater resources, but a fundamentally different approach to innovation. American industry in 1940 operated at a scale that Europeans found difficult to comprehend. Assembly lines that had revolutionized automobile production were being turned toward military application. Research laboratories at universities and private corporations were accustomed to rapid prototyping and iterative development. Most critically, there existed in American scientific culture a practical, empirical attitude, a willingness to try unconventional solutions, to fail quickly and learn faster. The British brought theoretical elegance. The Americans brought brute force problem solving and unlimited resources. The Proximity Fuse project was assigned to the Office of Scientific Research and Development under the direction of Vannevar Bush, a former MIT professor who would become one of the architects of America's military scientific complex. Section T, as it was designated, drew researchers from across the nation: physicists from Johns Hopkins, engineers from Bell Laboratories, specialists in radio technology from commercial broadcasting. They were given unlimited funding, top priority for materials and labor, and a single directive: make it work. The solution they developed over the next 2 years represented dozens of individual breakthroughs, each seemingly impossible, combined into a device smaller than a teacup. At its heart was a miniaturized radio transmitter and receiver, broadcasting a continuous signal and listening for reflections. When the shell passed near a solid object, an aircraft fuselage, a section of ground, a steel tank, the reflected signal would change frequency due to the Doppler effect. This frequency shift triggered a firing circuit that detonated the shell's main charge. The entire system, including 4 vacuum tubes each smaller than a man's thumb, a battery, an antenna, and the detonation mechanism, had to fit inside a space roughly the size of a Coke bottle. It had to survive being fired from a gun at accelerations that would turn a human body to pulp. It had to function in temperatures from -40 to +120 degrees Fahrenheit. It had to be reliable enough to work 95 times out of 100 and cheap enough to manufacture by the millions. Every component required reinvention. Standard vacuum tubes shattered under acceleration, so engineers developed new designs with reinforced elements and shock-absorbing mounts. Conventional batteries can survive the G-forces, so researchers created specialized cells that could function even after being subjected to forces that would liquefy mercury. The radio components had to be miniaturized beyond anything previously attempted, pushing the boundaries of 1940s electronics to their absolute limit. Each prototype failure, and there were hundreds, taught the engineers something new about the physics of extreme environments. By late 1942, they had a working design. The first combat deployment came not on land, but at sea, where secrecy could be more easily maintained. American cruisers in the Pacific, equipped with 5-inch guns firing proximity fuse shells, began reporting kill rates against Japanese aircraft that seemed impossible. Where previously a ship might fire hundreds of rounds to bring down a single kamikaze, now 3 or 4 shells often sufficed. The fuses detonated as they passed the aircraft, creating a sphere of shrapnel from which there was no escape. Japanese pilots, already facing the psychological burden of suicide attacks, now found themselves flying into a wall of intelligently detonating explosions. The effect on morale was devastating. But the Navy jealously guarded its new weapon. The fear was that if a proximity fuse fell into enemy hands, if a single unexploded shell landed somewhere it could be recovered and reverse engineered, the technological advantage would evaporate. So for 2 years, as American forces island hopped across the Pacific, as Marines died on beaches that might have been more easily secured with proximity-fused artillery support, the weapon remained restricted to naval use only, where duds would sink harmlessly into the ocean. The German army, meanwhile, had no inkling such a weapon existed. Their scientific establishment, though sophisticated in many areas, had taken a fundamentally different path. German research emphasized theoretical elegance and traditional methods. Resources were fragmented among competing agencies. The Wehrmacht, the Luftwaffe, the SS each maintained separate research programs, jealously guarding their findings. The Nazi ideology itself, with its rejection of Jewish physics and its emphasis on Aryan intuition over empirical method, had crippled German science. Many of the nation's most brilliant physicists, Einstein, Szilard, Teller, and hundreds of others, had fled to America, where they now worked to defeat their former homeland. Germany was fighting a 20th century war with 19th century methods, brilliant in execution, but obsolete in conception. The Germans had attempted to develop their own proximity fuse, designated the Kranich system, but the project had languished. German electronics industry, focused on radar and communications, lacked the mass production capability for miniaturized components. Resources that might have gone to such research were instead diverted to wonder weapons. The V-2 rocket, jet fighters, miracle technologies that Hitler believed would reverse Germany's fortunes through sheer technological intimidation. The proximity fuse, unglamorous and utilitarian, received little attention. This would prove a fatal oversight. December 16, 1944. The Ardennes Offensive, Hitler's last desperate gamble, smashed through American lines in Belgium. 3 German armies, 29 divisions, 250,000 men supported by tanks and artillery, drove westward through fog and snow toward the Meuse River. The attack achieved complete surprise. American units, many composed of inexperienced replacements or exhausted divisions sent to this quiet sector for rest, fell back in confusion. Within days, German spearheads had penetrated 50 miles into Allied territory, creating a bulge in the lines that would give the battle its name. In Washington, the decision was made. The proximity fuse, so carefully guarded for 2 years, would be released for use by field artillery. The risk of compromise was accepted as necessary. American forces needed every advantage to contain the German breakthrough before it reached critical supply centers. On December 22nd, the first proximity fuse shells arrived at forward artillery positions. Gunners received hasty instructions. Handle carefully. Set the fuse switch just before loading. Fire normally. They were given no explanation of how the fuses worked, only that they should aim for air bursts above enemy positions. The effect was immediate and catastrophic. For the Germans, artillery that had previously required careful range finding and precise timing suddenly became devastatingly effective. A battery of 6 American howitzers, firing proximity fuse shells, could achieve suppressive effects that previously required a battalion. German troops advancing through forests and villages found themselves subjected to air bursts that detonated at optimal height automatically, filling the air with steel fragments that shredded anything exposed. Defensive positions that would have provided excellent cover against ground-bursting shells offered no protection at all. The statistical transformation was stark. Casualty rates from American artillery fire increased by a factor of for almost overnight. German commanders, receiving reports on the front, initially dismissed them as exaggeration or battle fatigue. Shells that exploded in the air at the perfect altitude? Impossible. Artillery could not be that precise, that consistent. But as the reports multiplied, as officers witnessed the effects themselves, realization dawned. The Americans had developed something new, something that changed the fundamental calculus of combat. Klaus Müller, the observer who survived the barrage in the Ardennes forest, was not the only German soldier to experience this revelation. Across the bulge, from Bastogne to St. Vith, German units found themselves subjected to artillery fire of unprecedented lethality. A panzer commander described watching his infantry support, veteran troops who had learned to use terrain and cover to minimize casualties, being cut down in the open by shells that seemed to know exactly when to detonate. An artillery officer reported that his own battery, carefully positioned in a valley that should have provided defilade protection, was destroyed by American counter-battery fire that burst overhead. killing his crews where they stood. The psychological impact compounded the physical casualties. German soldiers had endured years of material inferiority. They were accustomed to American abundance of ammunition and fuel, to skies dominated by Allied aircraft. But this was different. This felt like fighting an enemy that possessed supernatural perception, that could see through forest and fog, that knew exactly where and when to strike. By early January, the German offensive had stalled. Multiple factors contributed. Stubborn American resistance at key road junctions, clearing weather that allowed Allied air power to devastate German supply lines, the arrival of Patton's Third Army from the south. But German officers, conducting post-battle assessments, consistently identified American artillery as a decisive factor. The proximity fuse had not won the battle alone, but had fundamentally altered the arithmetic of casualties and morale. German units that might have pressed forward despite losses instead went aground, pinned by artillery that seemed impossibly accurate. The psychological edge that German forces had maintained since 1940, the confidence born of superior tactics and battlefield experience, evaporated in the face of technology that made conventional tactical doctrine obsolete. The first intact proximity fuse fell into German hands in late January 1945, recovered from an unexploded shell near Foy. It was rushed to Berlin, where technicians carefully disassembled it under laboratory conditions. What they found confirmed their worst fears. The device was not merely advanced. It represented a level of miniaturization and manufacturing sophistication that German industry could not match. The vacuum tubes alone, each perfectly formed and shock-resistant, would have required months of development to replicate. The integrated circuit design, the battery technology, the radio components, every element was beyond Germany's current capability. Even if they had possessed complete blueprints and unlimited resources, German engineers estimated it would take 18 months to gear up production. By then, everyone knew there would be no Germany to defend. But the technological revelation went deeper than battlefield effectiveness. German scientists examining the proximity fuse understood that it represented not merely a clever weapon, but evidence of profound difference in industrial and scientific culture. The device had clearly been designed for mass production. Its components were standardized, its assembly straightforward. American industry had manufactured these by the millions, treated them as expendable, fired them without regard to cost. Germany had nothing comparable. German weapons, even late war designs, still bore the marks of craft production. Individual fitting, manual adjustments, an emphasis on quality over quantity that made sense in a pre-industrial age, but was suicidal in a modern war. The proximity fuse was designed by engineers who thought in terms of assembly lines, interchangeable parts, statistical quality control. It was a product not merely of different resources, but of a different philosophy. Some German scientists, studying the captured fuse in the final months of the war, came to understand something their military and political leaders never grasped. They were not merely losing to superior numbers or resources. They were losing to a society that had fundamentally different approaches to innovation, production, and the relationship between science and warfare. American industry did not craft weapons like precious artifacts. It stamped them out like bottle caps, millions of units, each one reliable, each one expendable. American science did not worship theoretical purity. It embraced empirical trial and error, rapid prototyping, the willingness to fail fast and iterate. These were not merely tactical advantages. They were expressions of a democratic, capitalist society that prized practical results over hierarchical authority, that rewarded innovation over obedience, that distributed decision-making rather than concentrating it. This realization that the war was lost not on the battlefield but in the fundamental structure of American society versus German society was too large, too terrible for most to accept. It implied that everything they'd fought for, everything they believed about German superiority and destiny, was built on false premises. So they did not accept it. They blamed betrayal, Jewish conspiracists, the overwhelming numbers of their enemies, anything except the truth, that they had been defeated not by who America was at war, but by what America was at peace. By the spring of 1945, proximity fuses were being used across all theaters of operation. In Germany, they devastated Wehrmacht units attempting to defend the Rhine crossings. In the Pacific, they protected landing forces at Okinawa from kamikaze attacks, detonating around aircraft with such reliability that Japanese pilots began to regard suicide missions as truly suicidal rather than heroic. In the final accounting, American forces fired over 22 million proximity-fused shells during the war. Production reached a peak of nearly 2 million units per month. The cost, in a war measured in hundreds of billions of dollars, was negligible. The effect was incalculable. But the proximity fuse was more than a weapon. It was a symbol, a physical manifestation of American industrial scientific power. Unlike the atomic bomb, which would later come to represent the apocalyptic potential of American science, the proximity fuse represented something different. The ability to apply overwhelming technological sophistication to even mundane problems, to mass-produce precision, to democratize lethality. It was not a terror weapon, not a city destroyer. It was a tool that made individual soldiers more effective, that reduced casualties among American forces while increasing them exponentially among the enemy. It embodied the American approach to warfare, not to match the enemy's courage or tactical skill, but it changed the nature of combat itself through technological innovation. German soldiers who survived the war carried memories of these weapons with them. In POW camps and hospital wards, in the ruins of cities they had once defended, they spoke of the shells that burst at precisely the right moment, that seemed to sense where they were hiding, that represented a level of technological mastery they had been told their enemies could never achieve. The proximity fuse became, in these accounts, emblematic of a larger failure. The failure to understand what America represented, to grasp that industrial democracy could outproduce military dictatorship, that free scientific inquiry could out-innovate centralized control. Some German scientists, particularly those who would later work for American programs during the Cold War, came to appreciate what the proximity fuse represented. In interviews conducted decades later, they spoke of it with something approaching awe. Not merely because it was clever, German engineering had produced many clever weapons, but because it was produced at scale, made reliable, distributed without regard to cost, and designed and beginning to be expendable. This, they realized, was how America fought wars, not by producing wonder weapons or brilliant tactical innovations, but by systematically solving engineering problems, mass-producing the solutions, and applying them with industrial efficiency. The proximity fuse never achieved the fame of the atomic bomb or the dramatic reputation of radar. It was too technical, too unglamorous. But professional military historians, examining the war's turning points, consistently identify it as one of the most decisive weapons developed by any side. General George Marshall called it, along with radar and the atomic bomb, one of the three most important technological developments of the war. Scientists who worked on the Manhattan Project later acknowledged that the proximity fuse, though far less dramatic, probably saved more Allied lives and contributed more directly to victory than the atomic bomb. It was deployed earlier, produced in vastly greater numbers, and affected the outcome of battles across multiple continents. The technology did not end with the war. Post-war guided missiles, surface-to-air defenses, even civilian applications and automotive safety systems all descended from principles first proven in the proximity fuse program. The organizational model used to develop it, bringing together scientists from universities and industry, providing unlimited resources for a focused objective, emphasizing rapid development over theoretical perfection, became the template for American military scientific projects throughout the Cold War. The Manhattan Project, the development of radar, the space program, all followed patterns established by Section T and its race to create a shell that knew when to explode. Picture Klaus Muller again, the German observer who survived the barrage in the Ardennes forest. He lived through the war, surrendered to American forces in April 1945, spent 2 years in a POW camp in Mississippi. There, in the strange cognitive dissonance of captivity in a land of abundance, he worked on a farm alongside other prisoners. The farmer who employed them, a man who had lost a son at Normandy, treated them with wary fairness. They were fed well, better. Muller realized with shame that he had been fed in the Wehrmacht during the final year of the war. In the evenings after work, Prisoners were allowed to listen to radio programs, to read American magazines and newspapers. Mueller read an article, translated by another prisoner who spoke better English, about the proximity fuse. By then it was no longer secret. The technical details were still classified, but the basic concept and its impact were public knowledge, celebrated as an American innovation that had helped win the war. The article included an interview with one of the engineers who had developed it. The man spoke casually about the challenges they had faced, the problems they had solved, the satisfaction of seeing their work deployed successfully. What struck Mueller, reading this account in a prison camp in Mississippi, was the engineer's tone. He did not speak of defending the homeland or destroying enemies or any of the ideological language that had saturated German military culture. He spoke of solving problems, of making something work, of the intellectual satisfaction of overcoming technical challenges. This, Mueller realized, was a fundamental difference. To the American engineer, the proximity fuse was a problem solved, a successful project, a practical achievement. To the German soldier who had experienced its effects, it was revelation and defeat. The same object, viewed through different cultural lenses, revealed entirely different worldviews. America had won the war not through hatred or ideology, but through pragmatic problem-solving applied at industrial scale. Germany had lost because it fought for abstractions, racial destiny, historical revenge, the glory of combat, while America fought to solve engineering problems and then go home. After repatriation to Germany in 1947, Mueller never spoke publicly about his war experiences. He became a teacher, married, raised children in a country being rebuilt from ruins. But he kept, in a drawer in his desk, a small fragment of metal, shrapnel from the barrage that had killed his battery. It was jagged, irregular, stamped with faint markings that indicated American manufacture. Sometimes, late at night, he would hold this fragment and remember the sound of shells bursting overhead with impossible precision. He would remember the moment he understood that the war was lost. And he would think about what the proximity fuse represented. Not merely technological superiority, but a different way of organizing society, of solving problems, of relating science to warfare and production to victory. The proximity fuse, in the end, was not just a weapon. It was a message, written in steel and electronics, and the blood of soldiers who died never understanding what killed them. The message was simple. Industrial democracy, for all its chaos and inefficiency and compromises, could outproduce and out-innovate military dictatorship. Free scientists, working in universities and corporate laboratories, motivated by professional pride and intellectual challenge rather than ideology, could solve problems that seemed impossible. A society that valued practical results over theoretical purity, that rewarded innovation over obedience, that distributed decision-making and encouraged individual initiative, could mobilize resources and talent in ways that centralized command economies could not match. German scientists had been brilliant. German soldiers had been brave. German industry had been sophisticated. But Germany had organized these resources according to principles that emphasize hierarchy, obedience, ideological purity, and craft production. America had organized its resources according to principles of mass production, empirical experimentation, decentralized innovation, and pragmatic problem-solving. The proximity fuse was the physical embodiment of these differences. It was not merely a better weapon. It was evidence of a better system. In the decades after the war, as historians analyzed why Germany lost, they identified many factors: Hitler's strategic mistakes, the two-front war, the Soviet Union's inexhaustible manpower, Allied bombing campaigns, intelligence failures. All true, but beneath these tactical and strategic explanations lay a deeper truth, one that German scientists studying captured proximity fuses had glimpsed in the war's final months. They had been defeated by a society that was fundamentally more effective at translating scientific knowledge into practical application, at organizing production for maximum efficiency, at mobilizing diverse talents toward common goals. They had been defeated, in other words, not by better ideology, but by better institutions. The shells that burst above the Ardennes forest in January 1945, killing Klaus Muller's comrades with such precise efficiency, carried within them the seeds of post-war order. They announced to those with eyes to see, that the future would belong not to nations that emphasize racial purity or military discipline or ideological fervor, but to nations that could harness science and industry through democratic institutions and market incentives. The proximity fuse was a weapon of war, yes, but it was also a preview of peace, of a world where technological innovation, mass production, and practical problem-solving would determine national power. This is why German scientists were shocked when America deployed proximity fuses and artillery. Not merely because the technology was advanced, not merely because it was effective, though it was devastatingly so. They were shocked because it revealed, with terrible clarity, that everything they believed about German superiority, technological, organizational, cultural, was false. They were shocked because a small metal cylinder, buried in the nose of an artillery shell, contained within it proof that they had already lost a war. Perhaps had lost it before it even began, lost it not on battlefields, but in universities and laboratories and factories where free inquiry and mass production had created capabilities that centralized dictatorship could never match. The sound of those shells bursting overhead, that sharp, precise crack that Klaus Muller heard in his final moments as a German soldier before becoming merely a survivor, was the sound of the old world ending, not with the apocalyptic finality of atomic weapons, but with the systematic, efficient, industrial conclusion that characterized American warfare. It was a sound of modernity defeating tradition, of pragmatism overcoming ideology, of democratic capitalism crushing military dictatorship through the simple expedient of being better at solving problems. And in the silence that followed, as snow continued to fall on the Ardennes forest and the last German offensive collapsed and the Third Reich entered its final agonies, that sound echoed forward into a future already being shaped by the lessons it taught. The proximity fuse had done its work. The message had been delivered, and the world would never be quite the same.